There is another way of looking at these, and that's hydrolysis. So let's take a look. Strong acids, what we say is strong acids like HCl, hydrolyze water. Completely. To form hydronium and chloride in this case. So this particular reaction, we don't expect much of the reverse. That's what these two arrows are representing. They're representing the forward and the reverse, but this is pretty much all forward. And so strong acids hydrolyze water like this. And in this particular reaction, water, actually, let me make sure I'm recording this. Yeah. In this particular reaction, HCl is the acid and water is the base. So we have a Bronsted acid-base reaction here, hydrolysis. For weak acid, like acetic acid, I probably shouldn't use these abbreviations, HAC. Probably should write it out. HC2H3O2. Weak acids only partially hydrolyze water. And so I'll draw two arrows here. And the small arrow going forward just represents the unfavored direction, and the big arrow represents the favored direction. And so there are different ways you could visualize it. One way I visualize this is, the forward arrow is going uphill, the reverse arrow is going downhill. So to go uphill, there's going to be quite a climb, but to go downhill will be a lot easier. And so that's how it's favored. Whereas over here, it's just completely down off a cliff here. That. And so what we'll say for strong acids, we have complete hydrolysis. And for weak acids, we have partial hydrolysis. Now, we know that the hydronium is much more stable than the hydrogen ion. And so when I look at this, the ionization reaction up here, where HCl ionizes into H plus and Cl minus, it's the same thing as the hydrolysis because the H plus is not going to stay like that. It's going to react with water. To make life a little bit easier, for us, I'm just going to ionize it. I'm not going to hydrolyze the acids. The acids, that is. All right, let's take a look at a non-electrolyte over here. And a non-electrolyte would be like, if it's not a strong acid, it's not a weak acid. Actually, what else are, before I go to non-electrolytes, what else are strong electrolytes? What else are strong electrolytes are the strong bases? And so we have the strong acids here, the strong bases. Now, there are some strong bases that you probably are familiar with. Can you tell me a strong base? Sodium hydroxide is a strong base. Yeah. And so an example of sodium hydroxide. Now, strong bases like sodium hydroxide are also salts. And the, I'm sorry? Yeah, yeah. And so what we have is we have a salt like this, and it's going to dissociate into sodium ions and hydroxide ions. Soluble salts are also strong electrolytes. So there are three things that are strong electrolytes. One, the strong acids. Two, the strong bases. And three, the soluble salts. Now the strong base is weird because it's not the soluble salt here. This is the strong base here. Strong base is aqueous hydroxide, like that. And what strong bases do is this. Strong bases hydrolyze water completely. When I say hydrolysis of water, hydrolyzed water just means it breaks apart the water. So we have hydroxide reacting with water. So in this case, hydroxide is our base and water is our acid. In the Bronsted acid-base reaction, the acid donates a proton to the base. And so hydroxide accepts a proton to form water, and water donates a proton to end up as hydroxide. So when you look at this hydrolysis reaction, was there any change? No. There's no change. So we know the 7 common strong acids, but are there 7 common strong bases? And it turns out there are more than 7. And so what we're going to do is we're going to look at these. So for example, the soluble hydroxides are 1. What are the soluble hydroxides? The soluble hydroxides are group 1, ammonium, calcium, strontium, and barium. Those are the soluble hydroxides. And so an example would be calcium hydroxide. Calcium hydroxide would be considered a strong base. But what about something like iron 3 hydroxide? Iron 3 hydroxide is not considered a strong base. This would be more of a weak base, even though it has more hydroxide. So iron 3 hydroxide is insoluble, only a little bit dissolves. Whereas calcium hydroxide is soluble, a more significant amount of it will dissolve. So what happens when calcium hydroxide dissolves is it's a salt. Soluble salts are strong electrolytes, and soluble salts will ionize completely. So if I have calcium hydroxide, which is soluble, it's going to form calcium hydroxide aqueous when you dissolve it in water. Now the calcium hydroxide aqueous will split up into calcium ions and 2 hydroxide ions. And the 2 hydroxide ions, this is what we consider strong base. So we have a lot of hydroxide in solution, where something like iron 3 hydroxide is not very soluble. So for something like iron 3 hydroxide, we aren't going to get very much hydroxide in solution, because not much of it dissolves. The soluble oxides are strong bases as well. Let me save this. So we'll just continue over here to the soluble oxides. Is that one of those that you remember from your solubility rules? No. But the soluble oxides are going to be like group 1 oxides. It would be like things like sodium oxide. Sodium oxide, the first thing is it's a soluble salt. I should have went soluble salts first. It's a sodium salt. All group 1 salts are soluble, and so it dissolves in water. And then we look at the electrolyte properties. It breaks up into sodium ions and oxide. This is a strong base. What do strong bases do? Strong bases hydrolyze water completely. So oxide will react with water to form what? Well, oxide is going to gain a proton, making hydroxide, and water is going to lose a proton, making hydroxide. So we end up with 2 hydroxides. And so oxide will hydrolyze water to form hydroxide. It's a strong base. What about rust, Fe2O3, solid? Would you consider this a strong base? No, this is not a strong base. Why? Because it's insoluble. It's an insoluble hydroxide. The soluble sulfides are strong bases, like this, K2S. Potassium salts are all soluble. And so if I had some solid potassium sulfide salt, I could dissolve it in water from K2S, aqueous. Since this is a soluble salt, soluble salts ionize completely. So I'd form 2 potassiums plus the sulfide. And here I have my strong base. And what do strong bases do? They hydrolyze water.
Can you say neutralize the iron and water?
I'm sorry?
Can you say that it's neutralize the iron and water?
Can you say it's neutralized in water?
Yeah.
Partially. Yeah. But not completely. Because what happens here is sulfide's a very strong base, and it will hydrolyze water completely to form what? Hydroxide and hydrogen sulfide ion. So what we're doing is we're replacing a more powerful base with a less powerful base. So sulfides is actually a more powerful base than hydroxide. So in that sense, it's neutralizing, but in another sense, it's not neutral. It's still extremely basic, because there's hydroxide in there. And so this is base hydrolysis of water. Sulfides do this. If you have an insoluble sulfide, then it's going to be a lot less basic. Does that make sense? Because the sulfide's not free. Uh-huh.
How do we know what kind of ions a reaction will make?
What?
How do we know what kind of ions these reactions will make?
How do you know what kind of ions these reactions will make? Because we look at it as being a Bronsted acid-base reaction. So this is the base, this is the acid. And in a Bronsted acid-base reaction, the base is a proton acceptor. So if you take S2 minus plus an H plus, we form HS minus. And the acid is a proton donor. So if H2O loses an H plus, we're going to be left over with an OH minus. And so that's how we know what forms. Normally when we see anions that end in IDE, it's monatomic, right? Like sulfide, oxide, chloride, bromide. It's monatomic. Sometimes we have ides that, like this one, that come from ammonia. So we have ammonia. Ammonia is interesting. Ammonia is what we call an amphoteric species, like water. An amphoteric or amphiphilic species, do you know what that is? Have you noticed that? Mm-hmm.
Sorry, what does that say?
This?
Yeah.
Amide, or amide. Both people. Both pronunciations are common. Amide, amide. I call it amide because it's like chloride, bromide, etc. And the base is ammonia. And so some species like water can act either as an acid or base. In these examples here, it's acting as the acid. Here. In the previous examples, it was acting as the base. Here. Water. And so water can go both ways. Ammonia can do the same thing. Ammonia can act as a base and gain a proton to form ammonium. Or it could lose a proton to form what? Amide. So amides are NH2 minus. Now, bases don't ionize. I should write that up here. Or dissociate. Bases do not ionize or dissociate. What do bases do? They hydrolyze. Bases hydrolyze. Whereas for acids, we can think of it as either way, you know. Can ionize, dissociate, hydrolyze. For salts, salts just ionize or dissociate into ions. So when amide hydrolyzes, we react it with water to form what? Ammonia and hydroxide. So in acid hydrolysis, we always produce hydronium. In base hydrolysis, we always produce what species? Hydroxide. Right. Now weak bases partially hydrolyze. Amide is a strong base. Ammonia is a weak base. And so when ammonia and water react, they don't react completely. They only react partially to form ammonium and what? Hydroxide. And so the difference between a weak base and a strong base is the amount of hydroxide it produces. A strong base like amide produces lots of hydroxide, whereas a weak base like ammonia produces very little hydroxide. So one way to try to visualize this, although maybe it's not, is if we have amide and water at the top of the hill, and you have a group, a large group, not all the amides, oddly enough, will have the same energy. You know, some of the amides will have lower kinetic energy, other amides will have higher kinetic energy, but all of them can make it downhill. So when we go from amide and water to ammonia and hydroxide, it's downhill. And the reason it's downhill is because there's a driving force. The driving force is going from stronger to weaker. So we're going from a stronger base, which I'll call SB, stronger base, to a weaker base. The weaker base is hydroxide. And this. WB. We're also going from a stronger acid, water, to weaker acid, ammonia. Ammonia is, you don't normally think of ammonia as being an acid, but some things can go both ways. Whereas when we try to visualize what's going on with ammonia and water, it turns out about 99% of these stay. Only 1% makes it here. And so this is the opposite. We're starting off down at the bottom of the hill and then climbing to the top. And let's say you have a population of bicyclists. You know, only this hill's so big, only 1% of them can make it up. That's one way to think about this. And so, a totally different situation. The amount of hydroxide is going to be much, much greater with a strong base than with a weak base. The same can be said about hydronium in acids. Strong acids produce a lot of hydronium, or H+. Weak acids produce very little, like acetic. I think I had it written out here. So lots of hydronium, very little. So this is the same situation. When we look at the driving force for these two, what we'll see is we're going from a stronger acid, SA, to a weaker acid, hydronium. Hydronium is a weaker acid. Whereas over here, we're going from a weaker acid to a stronger acid. Hydronium is a stronger acid than acetic acid. So over here, this is an uphill climb. In this uphill climb, only 1% or less population makes it up. But over here, it's a downhill climb. So even if the HCl doesn't have that much kinetic energy, make it downhill. And so this is about 100% end up downhill. Some might try to climb back up the hill, the opposite direction. The other ones were the soluble salts. You know, what the soluble salts do is they ionize about 100%. Ionize just means dissociate into ions. So we might have a soluble salt like iron 3 chloride. It's a solid. And then we dissolve it in water. So we get iron 3 chloride AQ. And then we look at its electrolyte properties. And what's going to happen is we expect this to ionize or break apart into iron 3 plus 3 chlorides. Soluble salts are strong electrolytes. What about insoluble salts? I'm sorry? Yeah, they're not very soluble in water. Let me change the volume. I just realized. So, give me an example of an insoluble salt.
Mercury.
Mercury what?
They do not soluble in water. They are heavy.
PB? When we dissolve or try to dissolve it, it stays mostly as this. But a tiny bit will dissolve because it's not 100% insoluble, and that tiny bit that dissolves will form ions. So let me show you one thing here. So PbCl2 doesn't form molecules, it forms ionic lattice like this. So to get this lattice to dissolve, you have to break apart the ions from one another. And so normally when we have an ionic solid, an insoluble one, a little bit dissolves, and that little bit that dissolves dissociates completely into ions. You know, otherwise we don't get it to dissolve away. And so we have something called the major species and the minor species. Over here, the major species are this. But with PbCl2, the major species would be this. When we write chemical equations, typically we want to write the major species in the particular equation. Okay, I need to go back up here for a second. So for weak, I'll just call this A here, since I use one. Weak acids. B, weak bases. And C, some heavy metal salts. Like PbCl4, something like that. These are weak electrolytes. Because some of these heavy metal salts have quite a bit of covalent type bonding associated with them. They're not purely ionic. Significant covalent. Covalent, as you recall, is the sharing of electrons in the bond. Which brings us to non-electrolytes. Non-electrolytes are everything else. So, for example, this one, what is this called? Methanol. Methanol is a non-electrolyte. It does not dissociate. And it doesn't dissociate because this is a covalent bond, not ionic. does not dissociate into ions. The molecules stay intact. So there's no like lysis. Lysis is like breaking apart the molecule. There's no methanolysis, where we break this bond here. And so methanol just stays as methanol. Uh-huh.
So in general, covalent bonds don't dissociate.
Yeah. Covalent bonds don't dissociate. That's a general rule. Covalent bonds do not dissociate. So, if you, I guess I was supposed to do that a little bit lower. Soluble salts was number 3 on strong electrolytes. So this is a little bit out of place. Let me try to move it. I'm not going to move it. Diamond, If we think about diamond, is diamond a strong electrolyte? Weak electrolyte or non-electrolyte? Non. Diamond's not very soluble either. What about quartz? Methanol. Quartz is, again, a covalently bonded lattice. We have 2 types of lattices. We have the ionic lattice, if it's soluble, then we have a strong electrolyte, and it breaks up into ions, aqueous ions in solution. If it's insoluble, then what should we call it? If the ionic lattice is insoluble, should we call it a non-electrolyte? And the answer is probably not. And so what some people call an insoluble ionic lattice is they call it a strong electrolyte of minimal solubility. So if we took that lattice and put it in water like this, most of the lattice stays intact, but maybe some ions break apart. Over here we have lots of ions. Here we have very little ions. As in the number. I should say very, not little, very few ions. And so if we have an ionic lattice, if it's insoluble, that doesn't mean it's 100% insoluble. It just means not that much dissolves. But when we look at what does dissolve, it ionizes completely. And so now we have 2 ways to define strong electrolytes and weak electrolytes. Oh, okay, thank you. The first way we can do it is based on conductivity. The second way we do it is based on ionization. So, an insoluble, if we do it based on ionization, then both the soluble and the insoluble ionic lattice are going to be strong electrolytes. Because the way it's defined is whatever does dissolve splits up into ions. And so this would be a strong electrolyte, and this would be a strong electrolyte, but there's going to be a huge difference in the number of ions. This has very few ions, this has a lot of ions. But since we have 100% dissociation into ions, whatever does dissolve, this represents a solid here that's not dissolving. But whatever does dissolve dissociates completely, therefore it's a strong electrolyte. That's one way. The other way of thinking about it is in terms of conductivity. These electrolytes, one of the things they can do is they can conduct electricity in water. And the more of the ions you have, the better it conducts. And so conductivity is given this symbol sigma. And sigma is equal to N mu Z. N is the number. Mu is mobility. And Z is charge. So we need three things in order to conduct electricity. We need a certain number of charge carriers, and they have to have mobility, and they have to have a charge. In metals, we have lots of electrons, and they have mobility, and they have a -1 charge. And so metals are good conductors of electricity. To see that here. This is our electrical conductivity apparatus here. Is air a good conductor of electricity? Not really. Why? Well, are there a large number of air molecules? Yeah, I mean, if there were no air molecules, you'd feel it. I mean, you wouldn't be able to breathe. And so, fortunately, there's air molecules in here. You can feel them. I mean, move your hand. Do you feel the air molecules? Yeah, you feel some air resistance. So this number, they have mobility. Are the air molecules moving around? Yeah, but what are they lacking? Yeah, they don't have any charge. Air molecules are neutral. And so this is what we call an open circuit. So, I have this plugged in. Electricity is trying to flow from one, we call this piece of metal electrode, to another piece of metal called the electrode. So we have two electrodes here.
Are humans
Humans conduct electricity. There's charge carriers. Humans. Yeah, that's why I want to be very careful, because if you get a large amount of current through your body, it could be lethal, deadly. So I'm going to be careful here. So air is not conducting electricity here very well. However, metals do conduct electricity pretty well. And so let's test this and see. Let's put the metal here. Let's see. You see anything? No. Let's crank up the voltage here. Okay, let me try this again. You see? Yeah. So metals conduct. And so this is called an open circuit. And when I put the piece of metal here, that closes the circuit. And what's conducting electricity in metals are electrons. Electrons, there are a lot of them in metals. They have good mobility. And they have charge. Charge is -1. Whereas plastic, you know, does plastic have electrons? Yeah, plastic has electrons, except the electrons in plastic, are they very mobile? No. They do have charge, -1, but if I put a piece of plastic here, it doesn't conduct electricity. And so what we call plastic is, we call it an insulator. It doesn't conduct electricity very well. No, the mobility of the charge carrier, it just has to, it could be any, it doesn't have to be electrons. It just has to have charge. And so we divide conductivity into 3 categories. The 3 categories are metallic conductivity. Metallic conductivity means it conducts electricity as good as a metal. And the standard is like gold and copper. You know, those are very good. And then we have an insulator. And then in between metallic and insulator, we have semiconductors. Which conduct a little bit. And so, based on conductivity, strong electrolytes have like metallic conductivity. Weak electrolytes have like semiconductor conductivity. And non-electrolytes would have insulator-like conductivity. But based on ionization, then it changes things. Because you could have a strong electrolyte with weak conductivity. So, you know, what's in tap water? Salts. And salts are strong electrolytes, aren't they?
Yeah.
But let's take a look at tap water. Probably should flip this on. You see it conducts electricity, but is that bulb very bright? No, it's kind of weak. So would you call the salts inside water a weak electrolyte? You know what salt is, the number 1 salt is in water? Sodium chloride. Would you call sodium chloride a weak electrolyte? Or would you call sodium chloride a strong electrolyte? Normally people call sodium chloride a strong electrolyte, but there's sodium chloride in here. But the conductivity is kind of weak. It's kind of weak because you want to see what sodium chloride looks like. Sodium chloride is a strong electrolyte, right? So I have some pure sodium chloride here. So with pure sodium chloride being a strong electrolyte, should it conduct electricity pretty well? Let's test it out.
No, it should be, I believe, in the water. Soluble in the water, or it's in the...
So then what do we call sodium chloride? Should we call sodium chloride a non-electrolyte, since it doesn't conduct electricity? Or what should we call sodium chloride? It needs water? Why does it need water? Sodium chloride is one of the best known. What's that? Yeah, better mobility. So it needs water because when we look at solid sodium chloride, the ions are locked into a lattice, and they have no mobility in the solid state. And so due to this lack of mobility, it's not going to conduct electricity. And so what I'm going to do is I'm just going to add some water, except I'm not going to add tap water. I'm going to add deionized water. And let's test our deionized water. Our deionized water should have no salts in there. So I need to wash this off. First, get a waste beaker. So I'm going to wash off the salts off here. The electrodes. And then test DI water. Hopefully our DI water does not conduct. If our DI water conducts, it's bad. Do you see any no. And so pure water doesn't conduct. Oh, why? Pure water doesn't conduct because it consists of water molecules, and there are lots of them. So we have lots of water molecules, and they're very mobile, but what do water molecules lack? Charge. There's no charge. And so sodium chloride is soluble. It's a soluble salt. All sodium salts are soluble. And when salts dissolve, what do? They ionize. They break apart into ions. That's how we get the lattice to dissolve into water. You got to break the ions from one another, freeze up the ions. I forgot to flip this on. And so this is salt water. Do you see how bright it is? So just because something's dim does not mean, this is tap water. Tap water has sodium chloride, but the concentration is very low. And so it's tricky. When we do conductivity and electrolyte, it's tricky because we could have a strong electrolyte, like sodium chloride, but at very low concentration. It gives poor conductivity. If you're defining just based on conductivity, you just look, how strongly it conducts electricity. Okay. Well, let's take a look at some other strong electrolytes here. So the question is, sodium chloride in the solid state, what should you call it? A non-electrolyte or a strong electrolyte? What should you call it? Well, it depends. I mean, it doesn't conduct electricity, so how can you call it a strong electrolyte? But then, if you eat it or dissolve it in water, then it conducts electricity very well. So, what definition we use is the one based on ionization. And so regardless of how well sodium chloride conducts electricity, I'll just call it a strong electrolyte, because if you dissolve it in water at high enough concentration, it conducts electricity well. That's it. And so we'll just call it a strong electrolyte. Uh-huh.
So it's like technically not really conductor by itself. So we put like non-conductor as an electrolyte, or
Are you filling out the report sheet?
yeah.
You don't have to fill out the report sheet for this one. Just do this in your lab notebook, take notes for this, and then that's what you're going to turn in. I have to modify this experiment quite a lot. And so we're not going to do everything on the report sheet. Have you ever tried to melt table salt? It's hard. If you've ever tried to melt table salt, it's pretty hard. But when you melt ionic lattice, do you know what happens? It breaks the ions apart so that they're no longer locked in a lattice position, and then they have mobility. There's a salt that's much easier to melt. Actually, there are a bunch of salts that are much easier to melt than sodium chloride. And so I'm going to try to melt one. Because if I melt the salt, then what's going to happen is it turns into molten liquid, and liquids have good translational mobility. And the salt I'm going to try to melt is not sodium chloride. The salt I'm going to try to melt is potassium chlorate. What's the formula for potassium chlorate? KClO3. And it looks like this. Do you see the white crystals? I'll put some crystals in there. Do I expect this to conduct electricity? No. Why? Well, it's got potassium ions, it's got chlorine ions, but what it's missing is mobility. So I'm going to put the crystals there, flip this on, and do you see any? No. Did I do this in Chem 4? Yeah. Actually, you guys already saw. Has everyone already seen this? You did this in Chem 4, right? Oh. Yeah, this is Chem 4 experiment. Well, I'll do it one more time. Just melt this. So we'd like to get a nice cone on there. And then normally when I heat something up and I want to be careful, I hold the burner in my hand. That way, if it starts reacting violently, I can move it away. I would probably just put this here. Do you hear that crackling? Does it have a smell? What does it smell like? All right, now it's molten. And so now it has mobility. This is potassium chlorate. One of the classic demos that sometimes what people do is that, have you ever seen the gummy bear in the exploding gummy bears? They throw gummy bears into molten potassium chlorate. Have you ever seen that? I'm not going to do that because it might be too dangerous. Here, what I'll do is I'm going to put a piece of paper. Potassium chlorate is a really strong oxidizer, and so if I get a piece of paper like this, let's see what happens to the paper. you know, there's heat also, but this is a little bit more than just the heat. So I'll get a little piece of paper and then drop that into my molten potassium chloride and see if anything happens here. No, it's not so molten anymore. Maybe nothing much is going to happen. It's just it's molten right at the electrodes. But just off the electrodes is still a solid. Let's see. Let me try this. This piece of wood here, not the match end side. Well, I'll have to demo it later. I'll do it in a proper demo in the hood. It's going to stay hot because of the electric current. The electric current there is causing the ions to move and keeping the kinetic energy. So what I'm going to do is I'm going to turn off the electricity for a second and let it cool down. So as it cools down, it's just going to re-solidify, and then I'll turn the electricity on. And do you see it stop conducting? But in this case, what I'm going to do is I'm going to dissolve potassium chlorate. Potassium salts are all soluble, and so I'm going to dissolve it in water. And what should happen? It should conduct. So let's see. I have to be careful here because I don't want to thermally shock the crucible and have it crack. Okay, now it's all right. All right, so you've seen these kind of things. The light bulb? No, yeah. We'll just do maybe... Okay, this is an example of a strong electrolyte. We'll just do...
Do you say for strong electrolytes that there are still like trace amounts of the full molecule for the minor species?
There could be, yeah. It might not be absolutely 100%. Wait. All right, so let's try sodium carbonate next. This would be another salt solution. Is it going to conduct? Put this on. Yeah. So soluble salts. What else are strong electrolytes? Strong acids. So unfortunately, the strong acid I have here is nitric acid. What's the formula for nitric acid? HNO3, and this is what it looks like. This is clean nitric acid. Sometimes it starts to discolor yellow, so this is pretty good. Strong electrolyte. What else are strong electrolytes? Strong bases. So I have some sodium hydroxide here. This is strong base.
Sulfuric acid?
I have sulfuric acid too, but this can do the same thing as nitric acid. So let's try the strong base. Sodium hydroxide, brightly lit. Okay, so the strong electrolytes are the soluble salts, strong acids, strong bases. Give me some weak electrolytes. there's some weak electrolytes. Nitrous acid would be weak, but I don't have any, unfortunately. We'll have to go with another weak acid. Give me another weak acid. Can you think of another weak acid?
Do you have hydrofluoric?
Hydrofluoric? Hydrofluoric is a weak acid, and we don't have any, fortunately. Because if we had hydrofluoric acid, I wouldn't want to touch it. But you know what I'd rather spill on me? I'd rather spill a strong acid like hydrochloric acid all over my hands than a weak acid like hydrofluoric acid. And it's not because of the acid. It's because of its metathesis properties. Hydrofluoric acid is very dangerous stuff.
Is it like the mercury?
Hydrofluoric acid? Hydrofluoric acid, fluoride loves calcium. And you have calcium in your blood, and you have calcium in your bones. So fluoride's a weak acid. So it penetrates your skin. It doesn't burn that much. But when it hits your bone, it precipitates. And when it precipitates calcium fluoride in your bones, it's supposed to be excruciatingly painful. But the problem is by the time it hits your bone, how long are you going to have to rinse your arm for? At least 15 minutes. 15 minutes isn't going to do it. You know. Even at least 1 hour is not going to do it. It's way too late by then. It's way too late. And so the people who work with hydrofluoric acid, like the semiconductor people, use it for etching chips. They have injection kits for hydrofluoric acid spills. If you spill a hydrofluoric acid, you're supposed to inject yourself with calcium glutamate or something like that. Yeah, or calcium succinate. Yeah. So otherwise, it's bad. If you want to see bad, and there have been a lot of accidents, go to Honeywell. Honeywell's one of the suppliers of hydrofluoric acid, and look at their pictures. They have a bunch of pictures of people who have hydrofluoric acid burns. You know, in their eyes, they got hydrofluoric acid splashing in their eyes. They look like zombies. You know, the white eyes. On their skin, on their face. Ooh. At UCSB, if you walk over to the electrical engineering department, they have the Wall of Horrors there. The Wall of Horrors are all the accidents that happened at UCSB alone, yeah. And they just take pictures of all the damage that they had. This is electrical engineering. So electrical engineers, all they have to take is Chem 1A, so they maybe don't have as much like wet lab experience, and so are maybe a bit more sloppy with their technique, you know. But yeah, the Wall of Horrors at UCSB. It was a fun place to visit and check out the pictures. But if you look at that Honeywell, then you probably won't want to work with hydrofluoric acid ever. Well, I'll work with acetic acid. In fact, I like eating acetic acid. Acetic acid is vinegar. So barbecue sauce is like vinegar and ketchup, so I really like barbecue sauce. But vinegar, fortunately, is not a strong acid. It's a weak acid. And so it's not as bright, but still not bad. So what else is a weak electrolyte? Weak base. And so I have some weak base here. The weak base that we're going to test is ammonia. Ammonia is normally gas, and so you'll probably start to smell it. Do you see it? What do weak bases do? What do weak bases do? Well, I'm sorry? Yeah, they accept protons, but in water, what do weak bases do? They hydrolyze, right. Weak bases do not ionize, they hydrolyze. And so I'm going to cover the ammonia, otherwise this is going to go flat. And so, the same thing with the hydrochloric acid. I should cover that, otherwise it will go flat as well. Okay, what else is a weak electrolyte? What else is a weak electrolyte are some heavy metal salts? A lot of lead salts have pretty colors. Do you know what this is? On the bottom? It's lead 2 iodide. Is lead 2 iodide soluble? No, it's insoluble. It's insoluble means very little will dissolve. But what does dissolve, does it stay intact as molecules or does it dissociate into ions? It dissociates into ions. And so what we should see is we should see very low conductivity just due to limited solubility. And so some people call lead iodide, a lead 2 iodide, like a strong electrolyte with limited solubility. And it lit it up. All right, how about ethanol? Aqueous ethanol. Weak electrolyte, strong electrolyte, or non-electrolyte? Yeah, ethanol should be a non-electrolyte. It's none of the above. It's not a hydroxide. So we're going to try some aqueous ethanol. Do you see anything? No. Ethanol evaporates quickly, so I'm not going to bother rinsing it off. It should evaporate off pretty fast. How about sugar water? Weak electrolyte, strong electrolyte, non-electrolyte? None. So sugar water, nothing. All right, so that's our review of so proper chemistry lab hygiene, you should wash your hands frequently to prevent stuff from getting into your mouth or eyes. Okay. What are you doing next? So I loaded a couple of PowerPoints this morning. You can download. And we're going to take a look at these PowerPoints. Yeah. Number 2, the composition, structure, properties, and reactions of a substance. This is chemistry. I just like to think the composition, structure, and properties of matter. This is from the dictionary, American Heritage Dictionary. So this is a dictionary definition. Chemistry, I just took it from there. Okay, when we think of properties, we have physical properties and chemical properties. Physical properties, normally we just think of a list of physical properties. What are some examples of physical properties you can think of? I'm sorry? Ice dissolving or ice melting? Ice melting, yeah. So melting point would be a physical property, boiling point, density, solid, liquid, gas. Those are physical properties. Give me some examples of chemical properties. Combustion. What else? How many different chemical properties can you list? Hmm? Solubility is actually physical. Let's say I have sugar water. Can I get the sugar and the water back out of that? Yeah. I could just evaporate the water. I'll be left with the sugar. In a chemical properties involve a chemical change. In a chemical change, I'm not going to get it back. And so combustion of sugar. If I burn the sugar or caramelize the sugar, can I get the sugar back? No. Whereas if I make sugar water, I can. And so solubility, it depends, though, it depends on what type of solubility, because some solubilities are chemical, like dissolving it in water would be physical, but dissolving it in acid might be chemical, because the acid might attack it and make something else. So if I take a piece of aluminum and dissolve it in hydrochloric acid, I'm not getting the aluminum back. I could evaporate the water, I'm just going to get aluminum chloride back, not aluminum metal back. And so we have those. And so what we're going to do is we're going to focus on just the chemical properties here. And so when we look at chemical properties, we want to look for patterns associated with the composition and structure of the matter to give us insight into the chemical properties. This is the kind of stuff I talked about earlier. Our approach to understanding chemical properties is going to be a mix of theory and descriptive. And sometimes it is easier not to. Theory would be great because then you don't have to observe anything. You just predict it. But theory is too complex sometimes. Like, for example, here, we can answer this question theoretically or by descriptive chemistry. Is HCl a gas? Can you do some theoretical calculations using physics to determine if HCl is a gas at room temperature, a liquid at room temperature, or a solid at room temperature? Yeah, you probably can use some physics to predict it, but how big of a project is that? It'd be huge. And so it's just much easier to memorize HCl is a gas in pure form at room temperature. I'm going to skip this slide. Skip this slide. So jumping through those slides here, we're just going to go here. How many different types of chemical properties are there? I think in Chem 4 we had combination, decomposition, acid-base, single replacement, double replacement, combustion, precipitation, acid-base neutralization. Remember all those? And then they had you memorize metal oxide plus water, metal oxide plus compound, this plus that. Did you have to do that? No? Okay. Well, what we're going to do is we're going to just look at this from a broader perspective. We're not going to focus on specific types of subcategories. We're just going to look at the major categories. And there's problems with this list, like combination, decomposition. And so when we look at the list, like this first reaction doesn't fit anywhere in that list. This is HCl plus nitrate plus gold. This is a very famous reaction. Do you know what this reaction is called? This one, people do this. They use this combination of acids to dissolve gold. And so people use this to dissolve gold. And when they dissolve the gold, if you evaporate the liquid, you aren't going to get the gold back, but people want the gold back. I mean, if you dissolve gold, you don't want to lose it, right? And so they get it back by using chemical means. That is, they use other chemical reactions to extract the gold. But this mixture of hydrochloric and nitric acid has a special name. Do you know the special name for hydrochloric acid and nitric acid? It's called royal water. Royal water is called aqua regia, so they call it aqua regia. And so this is aqua regia dissolving of gold. But we don't want, you know, to go into very specific reactions like this. How many reactions do you want to memorize? You know? And so this is why we're going to go more towards the theoretical part, because maybe more towards the theoretical part, we don't have to memorize reactions one by one. And as we go more towards the theoretical part, the way I'd like to categorize the reactions is based on, you know, common traits or common features between them. And so if we look at these two reactions are combination reactions here. We're combining carbon and oxygen to make carbon dioxide. Over here we're combining calcium oxide and carbon dioxide to make calcium carbonate. So both of these are combination because we're taking A plus B yields C, A plus B yields C. But these have totally different characteristics to them. And what are the characteristics? The characteristics are what I call the driving force for the reaction. And so these two are totally different in terms of that. This one up here is called a redox because it has a redox driving force. This one down here is what we call Lewis acid base because it will have a Lewis acid base driving force. And so what we're going to do is we're going to classify reactions based on that. If we look at aqua regia here, aqua regia is redox for nitric acid followed by, the hydrochloric acid is not there for an acid. Hydrochloric acid is for metathesis. So aqua regia works by redox first, followed by Lewis acid base. And so what we're going to do is we're going to classify the reactions into three basic types. 1, 2, 3. The three basic types would be metathesis. This is why I wouldn't want to spill hydrofluoric acid on myself, because fluoride loves calcium and it could cause some serious trouble. Fluoride loves calcium, it precipitates with calcium. Well, that's good for toothpaste, right? Because calcium fluoride is pretty tough, is resistant to acid attack. But it's not good in high quantities. Like, you know, the more is not necessarily the better. So if you have, like, you know, you don't want the extra strength fluoride toothpaste, because if you get the extra strength fluoride toothpaste, it'll start eating away your teeth. And you'll have mottled teeth. You certainly don't want it on your bones. And so we have metathesis. Metathesis are favorable ion combinations. Then we have acid-base. We have three types of acid-base reactions. Arrhenius. Actually, I might as well write this in here. There's a little preview. But I have to end the slideshow because I can't write on this. So metathesis. So when I look at hydrofluoric acid, I don't worry about hydrofluoric acid in an acid-base point of view. It's a very weak acid. I worry about it based on metathesis. I wouldn't worry about it on redox because it's not very reactive in terms of redox. And so if I'm looking at the chemical properties of HF, as an example, I would look at, one, I'd look at metathesis, I'd look at acid-base, and I'd look at redox. What types of reactions does it undergo and how reactive is it in these three categories? And then once I go through that, then I pretty much have my bases covered, these three bases. Well, speaking of acid base, we have Arrhenius, which is not that useful. The most useful will be Bronsted, Lowry, and Lewis. And then oxidation reduction or redox, so just redox reactions. Redox reactions, we have like combustion and other types, but I don't want to classify those as a separate category. I just want 3 types. We could have other types of reactions. We're talking about CFCs. CFCs are photochemical, creating free radicals, etc. These 3 categories, you know, I want to approach it more from a theoretical because I don't want to, again, memorize them one by one. And so these 3 categories are based on the driving force. The driving force is a formation of more thermodynamically stable products from less stable reactants. So what we want to do is we want to go downhill in energy, thermodynamic energy. Okay, and that's how we're going to divide these, because we look for different things in each of these types of reactions. What is more stable? You know, what is more stable in terms of metathesis? What is more stable in terms of acid base, and what is more stable in terms of redox? They're different. And so that's why we don't mix and match. All right, so I'm going to stop here. Let's take a break for 15 minutes, and then let me continue this after the break. We'll resume here. All right, for driving forces, you know, theoretically we could calculate it, but what we're going to do is we're just going to use descriptive clues or indications that we're going from less stable to more stable. In metathesis, there are 3 things we look for in stability. One is like a precipitate, and so precipitation is a driving force. 2 is gas formation. These are things we talked about already, I think. And 3 is stronger acid to weaker acid, so SA to WA. For acid-base, it depends on what type of acid-base reaction we're looking at. For Bronsted, then it's SA to WA or SB, stronger base to weaker base. That goes for metathesis as well. We could look at the base. But for Lewis, it's more complicated. The reason Lewis is more complicated is because there are many more Lewis acids than there are Bronsted. In fact, all Bronsted acids qualify as Lewis, but not all Lewis acids qualify as Bronsted. So Lewis acids encompass the whole acid-base universe. So if this is the acid-base universe here, then Lewis defines all of them. Bronsted is just a small part of the acid-base universe, so Bronsted would be like this. We could use Lewis to analyze all acid-base reactions, but since it's more complicated, it's just easier to look at a subcategory of these. And the subcategory of these would be Bronsted. SA is stronger acid to weaker acid. To weaker acid. And then finally we have redox reactions. For redox, we have a simple driving force. We're just going from stronger OA to weaker OA, where OA is oxidizing agent or oxidizer. And stronger RA to weaker RA. And so OA is oxidizing agent, RA is reducing agent or reducer. So those are the types of things we look for. We're not going to calculate it theoretically. So our objective is to better understand chemical properties. Chemical properties are often overlooked in general chemistry. And we'd like to understand it to the point where we can predict potential chemical reactions between substances. So when we look at this, we're not going to subcategorize them. We're just going to look at the three broad categories: redox, acid-base, and metathesis. When we look at redox, there are different types of redox reactions. There's single replacement, skeleton, redox chart, combustion. So I forgot to put combustion in there. For acid-base, we focus on Bronsted and Lewis. Arrhenius is very small. For metathesis, we look at ion combinations, double replacement, etc. When we do these predictions, we make some basic assumptions. That is, we want concentrations around 1 molar and gases at about 1 atmosphere or 1 bar. Extremely low or extremely high concentrations may require compensating for. So if we do this reaction, here at 1 molar, we get a precipitate. But at very dilute concentrations, we might not get any precipitate. If we do the reaction here under normal conditions there, we get no reaction, NR. But if we use hot concentrated nitric acid, we get a reaction. Sometimes if we add excess, too much of something, we get different types of reactions occur. And so here, this precipitation reaction, which is lead 2 hydroxide, turns into something else entirely. And so, these are just rules. There's exceptions to rules. The thermodynamic driving force is just one of the aspects we're looking at. Really, we should look at something called kinetics. So to properly predict reactions, we must understand the kinetics of the reaction as well. Kinetics is how fast the reaction occurs. So there's a driving force here. Diamond is less stable than graphite. So we're going from something that's less stable to something that's more stable, but diamonds are going to last pretty much forever because it's so slow, this transformation process here. And so graphite is what we call more thermodynamically stable, but the kinetics of this dictate that the diamond is fairly unreactive, and therefore we call it metastable. It should decompose, but it doesn't, and so there's metastability. So the goal for metathesis is to find favorable ion combinations. The easiest is to do double replacement. Double replacement, you're swapping the ions and see if you get a more favorable combination. So we look for these three driving forces again. We also have to watch out because some things don't look like metathesis, like aqueous ammonia. Aqueous ammonia, you got to remember that weak base is partially hydrolyzed water. So aqueous ammonia hydrolyzes water to form ammonium ions and hydroxide ions. Those ammonium ions and hydroxide ions can participate in metathesis. So we're going to do a couple of things here. One, okay, for today's lab, this is what you're going to turn in. You could do it this way. You can just write it in your notebook. It's fine. Or Yeah, just write it in your notebook or something, and then scan it as a PDF and upload it. But you're going to write the solubility rules, just to remind yourself, refresh your memory of the solubility rules. And then, if we're looking at stronger to weaker acid, we're looking at these, but you have to remember of the, what did I call that? You know, all the strong acids in water have the same strength. Do you recall me saying that? Right, right. And so the strong acids have something called the leveling effect, right? Leveling, I think. As do the strong bases. There's a leveling effect here.
Should we be writing it down or are you gonna post the discussion?
I'm going to post this. And so we treat all the strong acids the same strength. We treat the strong bases the same strength. The weak acids we don't. Talked about electrolytes. These are the gas formers here. All right, so the first one we're going to do is calcium carbonate and sulfuric acid. Here we want to write the complete equation. C stands for the complete equation. And then we want to write the ionic equation. And then we want to write the net ionic equation. So of calcium carbonate and sulfuric acid, that's one. The next, I'm probably going to move. Actually, I don't want this one. What do I want to do? I'm going to change this one. We'll go potassium fluoride and acetic acid. That's the next one. Lead iodide and hydrochloric acid. Another. I'll just put these all on one slide. So. I'm sorry? Yeah. Magnesium nitrate and aqueous ammonia. This is the lab you're going to turn in. At the end of class. Actually, just do this on paper and then turn it in at the end of the class. No, we're doing these here.
So will we also have the solubility?
Actually, you can skip writing the solubility rules. Just do these reactions here. See, that's 4 reactions. Don't tear out any pages out of your lab notebook. If you need paper, I have some paper. Why don't you guys work on these? I'll go get it. Let me go. I have some paper here. And you could work with others on this as well. All these are double replacement, except for the last one. The last one is sort of double replacement. But 1, 2, and 3 are double replacement. 4 is double replacement, but it looks a little different.
For the first one, since carbonic acid is like a weak acid and it's unstable, do you want us to write carbon dioxide gas and
Yeah, so the question is on the first one, carbonic acid is unstable. If it's unstable, I don't want you to write it there. I want you to write the carbon dioxide gas and water.
so you want us to write the full equation?
Yes, yes. And so the first one, yeah, don't write carbonic, write water and CO2. Did I record this? Yes. Non-aqueous states. Are you talking about the states? I only do the non-aqueous states. So for example, calcium carbonate, what's the formula for calcium carbonate? CaCO3. Carbonates are all insoluble except for group 1 ammonium, so I write it as solid. You have to write it as solid. I write aqueous blank. So for example, sulfuric acid, I don't write any state. Because if I write, sulfuric acid is H2SO4, and I leave no state there, that's fine. You could put aqueous or you could just leave it blank, just for the aqueous, but everything else you have to write. And this is going to form what? This is going to form carbonic acid, H2CO3, but don't leave H2CO3 in the equation. You have to decompose it. And the way most people decompose it, they'll just write an arrow here showing it decomposes into H2O liquid plus CO2 gas. So immediately when it forms, it'll decompose. And what's the other product of this? Well, we have carbon dioxide and water, and then what's the other product? Calcium sulfate. Sulfates are all soluble except for silver, lead, mercury, calcium, strontium, barium. So calcium sulfate is an insoluble solid here. And so this is what we call the CE. And then we need the driving force. What is the driving force, if any? So one driving force is this. We're going from a stronger acid, sulfuric acid, to a weaker acid, The weaker acid would be carbonic acid or CO2. And so that's a driving force. Now, this precipitation, we don't know if this is a driving force. The reason we don't know if that's a driving force is because we're sacrificing one precipitate for another. And so the reason there's a question mark here is because we have this precipitate versus this precipitate. Which precipitate is more stable? Or which solid is more stable? If there was no solid on the left, that is, if both of these were aqueous, then the precipitation would be a driving force. But what we're doing is we're sacrificing one solid for another. We don't know if the new solid is more stable or less stable. Does that make sense? So this is what we call solid to solid. Solid to solid you don't have in Chem 4 or Chem, high school Chem, because it's too complicated. So they don't put these there. So the precipitation here, how can we tell which one's more stable? Well, we base that on solubility. The one that's more stable is the less soluble one. And so that we could take a guess at that using some bonding, but it might not be so easy. So for sure, all we need is one driving force, and we already have that. And so it doesn't matter what this is, whether it's a driving force or not. When you go to the ionic equation, you only ionize the strong electrolytes. Is calcium carbonate a strong acid? No. Is calcium carbonate a strong base? No. Is calcium carbonate a soluble salt? No. So leave it alone. Do not ionize. People have a tendency to ionize all salts, but we don't. Is H2SO4 a strong acid? Yes. So we ionize it. When we ionize it, it's a diprotic acid, but only one proton breaks off at a time. So if we break off one proton, we're left with H plus, the proton, plus HSO4 minus, bisulfate. Is bisulfate a strong acid? And so this is a two-step process. Both protons don't break off at the same time. You know, this is like, you know, you might have good mobility if you have both your arms, but if one arm gets chopped off, do you still have good mobility? Maybe not as good, right? And so in this case here, what happens is one proton breaks off and we're left with HSO4 minus. Is HSO4 minus bisulfate one of the 7 common strong acids? And therefore we treat it as weak. And so H2SO4 only breaks off one proton easily. The second proton is kind of stuck on there. Does that make sense? So rather than this is the most common mistake. The two most common mistakes are, one, people ionize calcium carbonate. No. 2, people ionize sulfuric acid into 2H plus a sulfate. 2H plus a sulfate's wrong. It's only 1H plus a bisulfate. No, I wouldn't accept that, right? It's wrong. Just the first. The reason is the proton breaks off one at a time. So you need to know this. It's a stepwise process. So after the first proton breaks off, it does it completely because H2SO4 is a strong acid. And then we look at the second proton. Will the second proton break off? No, because it's a weak acid. How about H2O? Does H2O ionize? CO2, calcium sulfate. Is calcium sulfate a strong acid? Strong base? Soluble salt? And so we leave it alone. And when we look at this, there are no spectators to eliminate. So the ionic equation and the net ionic equation are the same. The difference between the ionic and net ionic is we get rid of the spectators, but there are no spectators here. And this would be done. Mm-hmm. How does it lose? Well, we have to think in terms of electrolyte properties. What's taking the H plus off the acid? What's taking the H plus off the acid is water. And so there's a tug of war here between water and sulfuric acid. Who wins? Water wins. Water takes the H plus and makes hydronium. Then water tries to take this proton off and it can't. And so this proton's stuck on there because water can't pull it hard enough. However, water can't take that proton off, but you know what can? Calcium ions. Calcium ions can take that proton off and react with the sulfate. And this happens on the surface. So if the bisulfate hits a calcium ion, then the calcium ion displaces or knocks off the proton and forms a sulfate. And so over here, there's no hydrogen here. It was knocked off by calcium. All right?
Can you scroll up for me just a little bit so I can see the
It already did. It took out the other proton. This is before mixing these two together. Before mixing these two together, these are the chemicals that we're going to mix together. We're going to mix some solid calcium carbonate and some sulfuric acid. When we look at the beaker of sulfuric acid is a strong electrolyte, so inside that beaker are these. And so the way I think about this is like this. The way I think about it is this is what you buy at the store. You go to the store, you buy some H2SO4, and you get a beaker of H2SO4. Inside that beaker of H2SO4, we're going to find hydrogen ions and bisulfate ions. And so that bottle of H2SO4 actually consists of hydrogen ions or hydronium and bisulfate, primarily. Over here, I'm going to buy a jar of calcium carbonate. The jar of calcium carbonate is just going to consist of this white, solid calcium carbonate. And then if I went to go buy carbonic acid, I'm not going to get any carbonic acid. Instead, what I'm going to get is water and CO2. In fact, you can't go to the store to buy carbonic acid. Why? Yeah, because it's too unstable, it'll decompose. So even if they tried to make carbonic acid, it's going to decompose into water and CO2. So you'd end up buying water and CO2. Calcium sulfate you can get, you know. So these are all before mixing. And then I mix it and see what happens. So what I'm doing is I'm mixing the calcium carbonate with hydrogen ions and bisulfate, and the calcium ions are going to knock the other hydrogen off and create calcium sulfate. All right, just keep working on these. This should be potassium. I don't want solid potassium fluoride. This one's going to be aqueous. And down here, this is not going to be solid magnesium nitrate. We're just going to go with aqueous magnesium nitrate. You could work with other people, like, or at least compare your You can compare your equations with what other people are getting.
So you have about 35 minutes. Or, what time do you get out? 50 or 55? 50, yeah, 35 minutes.